We're going to go through regression models. We've talked about the three types of regression models that we've learned. Linear, which is our y equals mx plus b. Quadratic, which is y equals ax squared plus bx plus c. That's the standard form. And then exponential, which is y equals ab to the power of x. We've also talked about when we have data, the three ways we can decide if something is linear, quadratic, or exponential. We can take first differences, will tell us if it's linear. Then the second differences from the first differences will tell us if it's quadratic. And first ratio, which is something different where we do division, will tell if it's exponential. So let's start with first differences. We take the bottom number and subtract the top. 9.2 subtract 10.1 gives us negative 1.1. 8.2 subtract 9.2 gives us 1. Sorry, negative 1. 7.3 subtract 8.2 should give us negative, I think, 1.1 again. And 6.4 subtract 7.3, one more time, negative 1.1. Good, because we actually made an error the first time we went through this. So if we look, our first differences are almost identical. We have one that's a little out of place. What we're going to do from there is we're going to plot them to make sure that they make sense. Our first coordinate is 5 and 10.1. So we go to 5 and 10.1 would be approximately there. 6 and 9.2. 6 and 9.2. And then we can see from here we have 7 and 8.2. 8 and 7.3. And 9 and 6.4. So again, this looks best represented by a straight line. So it's most likely this represents a linear model, or a linear model represents this regression the best. Okay? So we didn't actually have to go into our second differences and first ratio because on our first try we figured out that this was linear. Let's go to our next example. Our next example, we're going to do the same thing. We start with our first differences. So negative 5.3 subtract negative 6.3. Okay? And that should give us 1. I apologize. I just switched something very quickly so that this does work for what I wanted to do. So negative 8.3. Okay? That becomes 3. Then we take negative 4.4, subtract negative 5.3. It looks like an equal sign. Let's try to fix that. I'm just trying to squeeze it all in here. Negative 5.3. Okay? And that's going to be roughly 1.1. We're going to take negative 5.4, subtract negative 4.4. And that is negative 1.
5.4. We get 5.4.
Right here. That's where I got 5.4. And then negative 8.3, subtract negative 5.4. Gives us about negative 2.9. I think that's right. Yeah, negative 2.9. So looking at linear, these are not consistent, right? This doesn't really work. So we move on to our second differences.
Wait, so the first ratio
is when you divide them. We'll get to that.
Exponential.
So 1.1 subtract 3 is almost 2. I think it ends up being 1.9. Negative 1.9. Negative 1 subtract 1.1 is negative 2.1. And negative 2.9 subtract negative 1, so that's like adding, is negative 1.9 again. So, if we look at this, these ones are much closer than our linear models. They all look like they're about 2, okay? So let's see if we can graph these points, because we think we found something here where these second differences are really, really close to being consistent. So let's see if we can plot our points here and if it'll fit our quadratic model. So negative 5 and negative 8.3. Negative 8.3 is about there. That's our first coordinate. Negative 4 and negative 5.3. Negative 4 and negative 5.3 is about here. Negative 3 and negative 4.4. 4.4 will be about there. Negative 2, negative 5.4. You knew it? And the last one is negative 1 and negative 8.3 again. So it looks like a parabola fits this pretty well. It may not be perfect, but it's probably the best out of the three models we have to fit this regression. So we would say this relationship is quadratic. And going by what we're doing, could probably assume. But let's test out our last one. We'll quickly go through first differences. 7 from 9 is negative 2. 5.2 from 7 is negative 1.8. 3.9 from 5.2 is negative 1.3. I think that's supposed to be 3. Yeah, that's not supposed to be 3. That's supposed to be 3. So 3 subtract 3.9 gives us negative 0.9. So these here aren't quite changing by the same amount. We went from negative 2 all the way down to negative 1, each time decreasing. Most likely this is not a linear relationship. We'll try our second differences, which we did before. Negative 1.8 subtract negative 2. It's the same as positive 0.2. Negative 1.3 subtract negative 1.8. Positive 0.5. And then negative 0.9 subtract negative 1.3. Positive 0.4. This isn't bad. If we take a look, they're not as close as our last model, but they are pretty close. Okay? We can't be definitive. Before we knew we had a parabola, so we could be very definitive of what we were doing. Let's plot these and take a look. 1 and 9, 2 and 7. Is that right? 1 and 9, 2 and 7, 3 and 5.2. 3 and 5.2. 4 and 3.9. And finally 5 and 3. Okay. This could possibly be fit by a parabola if from this point on it makes a turn. Right? Because we know parabolas have to eventually come back up. But going from this information, we can't be definitive about it. We can't say for sure a parabola is the best fit. So what we're going to do is we're going to try our first ratios to see if maybe they will be a better fit. Because you know our exponential and our quadratic are very similar. So we take the second value and divide the first. 7 divided by 9. I'm going to take our answers right out of here. We get 0.8. 5.2 divide 7. Going to give us 0.7. 3.9 divided by 5.2. Is it not? I think it's 0.8 again. 0.8. And finally, 3 divide 3.9 ends up being 0.8. So, in comparison, it looks like our first ratio is a bit of a better fit than our second differences. Okay? So it's important that we actually carried out both. And this definitely, relationship looks like it could be exponential decay, where it's slowly decreasing more and more. So we're actually going to call this a exponential model in the end.
What does exponential even mean?
Growing or decreasing by a growing or decreasing rate.
Oh, okay.